Let's think about how we can penalize trees. If you remember, when we were doing linear regression, we could simply penalize the size of the parameters, either by adding up their absolute values or by adding up their squared values, something like that. Now, when we have a complicated decision tree with loads and loads of different leaves at the bottom, like we had probably, I don't know, thousands in that decision tree we just did in R, how can we penalize this decision tree so that when the algorithm is deciding whether or not to make another split, it's a little bit more careful about generating leaves? Well, it's kind of obvious. Add to your loss function a cost per leaf. So imagine we have the loss function, and the loss function is R at the moment. What we'll do instead is think about a loss function which also takes into account the number of leaves, and we're going to add a penalty per leaf. That's getting a bit messy, just let me write that out again. This over here counts the number of leaves, and so we say our penalized loss function, which depends on alpha, just like previously the penalized loss function depended on lambda. The penalized loss function equals the original loss plus alpha times the number of leaves. Let's think a little bit carefully. What happens when alpha is 0? You should be able to figure out what kind of tree we're going to get. Go on, you can do it. Alpha equals 0, the last term drops out, we're just going to get their incredibly complicated tree. What happens if alpha is massive? Well, if alpha is massive, the first time it tries to make a split, well, maybe the loss function, the mean square error, might reduce by, maybe it wants to go down by 3, which would be very impressive, for example. But if alpha is 10,000 or some other ridiculously high number, it's going to be 2 extra leaves because there'll be 1 extra leaf because we split a leaf into 2. There's just no way it's ever going to make a split. And quite clearly, we can now have again on our x-axis the complexity of the trees, a very simple model, alpha equals huge, a very complicated model, alpha equals 0, in exactly the same way that we had for lambda, and hopefully we're going to get some kind of train invalidation curves. We know the train curve goes all the way down to around about $4,000 mean absolute error. Hopefully we're going to find that there's some kind of trade-off where the validation MAE keeps on going down, but then it starts going up before it reaches that awful level of 20,000, which we had for the most complicated tree. If we can find that sweet spot for the optimal complexity, then we're in a good space. So let's see if we can do that.